Welcome! In this session, we will tackle LeetCode problem number 2056, number of valid move combinations on chessboard. This problem challenges us to compute the total number of valid move combinations for multiple chess pieces on a chessboard, considering their movement constraints and the board's boundaries. Let's dive in. Let's continue. The problem we're tackling involves an nxn chessboard and a set of chess pieces placed at specific starting positions. Each piece moves according to its standard rules, like how a rook moves in straight lines or a bishop moves diagonally. Our goal is to calculate the total number of valid move combinations for all pieces, or a move combination is valid if no two pieces end up on the same square and all moves respect the movement rules of the pieces. Essentially, we're determining how many unique configurations are possible after all pieces make one simultaneous move. To solve this problem, you'll be given two main inputs. The first is an array called pieces, which lists the type of each chess piece, such as rook, bishop, or queen. The second input is a 2D array called positions, which specifies the initial positions of these pieces on the chessboard. These positions are 1-based, meaning the top left corner of the board is represented as 1, 1. Once we process these inputs, our solution needs to return an integer that represents the total count of all valid move combinations. Here are some examples to help clarify. In the first example, we have two rooks starting at positions 1, 1, and 1, 2. Each rook can move horizontally or vertically, and we need to count all valid combinations of their moves, ensuring they don't end up on the same square. In this case, the total number of valid move combinations is 23. Another example involves a single queen starting at position 1, 1. Since the queen can move in 8 possible directions, horizontally, vertically, and diagonally, we calculate all valid moves for this piece on an 8x8 chessboard, resulting in 64 valid combinations. In the third example, we consider a bishop starting at position 4, 3. A bishop moves diagonally, so we calculate all possible moves within the bounds of the chessboard for this piece. Each valid move is treated as part of the total, and in this case, the number of valid move combinations is 256. These scenarios illustrate how different pieces and their movement rules contribute to the total count of valid combinations. When solving this problem, there are several constraints and edge cases to keep in mind. First, the number of pieces will range from 1 to 4, and their initial positions will always be unique. The chessboard is fixed at an 8x8 size, so any moves that go beyond its boundaries cannot be counted. For cases with multiple pieces, it's critical to ensure that no two pieces ever occupy the same square after moving. Finally, for computational efficiency, the solution must handle the maximum scenario of 4 pieces while still ensuring accuracy in the calculation of all valid move combinations. To tackle the problem of calculating the number of valid move combinations on an nxn chessboard, we start by considering the brute force approach. The idea here is to generate all possible move sequences for the given chess pieces, which may include rooks, bishops, knights, or others, each following their own movement rules. Once these sequences are generated, we filter out any combinations where 2 or more pieces end up on the same square, or where a piece moves out of bounds. To break it down, the steps involve generating all moves for each piece, iterating through every possible combination using nested loops, and validating each one to ensure there are no collisions or invalid positions. However, the major drawback of this method is its factorial time complexity, as the number of combinations grows exponentially with the number of pieces and their possible moves. This makes brute force impractical for larger boards or more complex scenarios. A more efficient method involves backtracking with pruning. Instead of generating all move combinations up front, this approach systematically explores the solution space piece by piece, pruning branches as soon as they become invalid. For example, if a move results in a collision or places a piece out of bounds, we immediately discard that path and backtrack to try a different move. This drastically reduces the number of states we need to explore. Key to this approach is leveraging the movement constraints of each piece, like the straight-line movement of a rook, to limit the search space. Additionally, we maintain a set of occupied squares to quickly identify conflicts as we progress. The process involves representing the board as a 2D array, simulating moves recursively, validating each move at every step, and backtracking when necessary. While this approach is still exponential in the worst case, pruning invalid states early makes it significantly more efficient than brute force. An alternative solution could involve dynamic programming, where we pre-compute the reachable positions for each piece and iteratively build valid combinations. For instance, we might first calculate all valid positions for one piece, then combine those with the valid positions of another piece, and so forth. While this has theoretical potential, the complexity of implementation and the need for extensive pre-computation makes it less intuitive and less practical for this problem. After evaluating these approaches, backtracking with pruning emerges as the preferred strategy. It balances efficiency and simplicity, avoiding the exhaustive computations of brute force while remaining easier to implement than dynamic programming. The trade-offs are clear: brute force is simple but computationally infeasible, dynamic programming is elegant but overly complex, and backtracking strikes the right balance, allowing us to solve the problem effectively even for larger boards and more pieces. The problem we're solving involves determining how many valid move combinations can be made for multiple chess pieces on an n-axis chessboard. Each piece adheres to its own unique movement rules, such as rooks moving horizontally or vertically, or knights moving in an L shape. Importantly, no two pieces can occupy the same square at any time, and all pieces must stay within the bounds of the chessboard. The input specifies the size of the board, the types of pieces, their initial positions, and the number of moves allowed. These constraints lay the foundation for our algorithm, ensuring that all moves adhere to chess rules and that we account for the interplay between pieces as they move across the board. To tackle this problem, the first major step is simulating all possible movements for each chess piece. This requires understanding the movement rules for each type of piece: rooks move vertically or horizontally, bishops move diagonally, and knights move in an L shape. For each piece, all possible moves over k turns must be generated, ensuring that moves remain within the bounds of the board and that pieces never occupy the same square. Backtracking is then used to explore all combinations of moves. Starting from the initial positions, the algorithm recursively generates each piece's moves turn by turn, while tracking the positions of all pieces to maintain validity. By incrementing the count whenever a valid combination is identified, we systematically explore all possible configurations. Next, we optimize the process by pruning invalid states as early as possible. For example, if a move takes a piece out of bounds, the algorithm immediately backtracks from that state. Similarly, if two pieces occupy the same square, the current sequence is discarded. Memoization is another key technique here, as it allows us to store and reuse results of previously explored states, reducing redundant computations. By combining these techniques, we not only ensure the correctness of our solution but also significantly reduce the computational overhead. Finally, a counter tracks the total number of valid move combinations, which is returned once all possibilities have been explored. Several key insights emerge from this approach. First, the unique movement rules of each chess piece mean that pre-computing all possible moves for a given piece at a specific position can simplify the recursive logic. Second, avoiding collisions between pieces is critical, and using a set to track occupied positions enables efficient checks. Additionally, pruning invalid states early, such as out-of-bounds moves or collisions, is essential for reducing computational cost. Backtracking is central to the algorithm's design, and its efficiency is greatly enhanced by using memoization to avoid exploring the same state multiple times. Finally, the use of specific data structures such as sets for occupied squares, queues or recursion stacks for move simulation, and memoization tables ensures that the algorithm is both efficient and scalable. Analyzing the complexity of the solution, the time complexity in the worst case is proportional to the number of states explored. With m pieces and k moves, there can be up to n squared m asterisk k states. However, pruning and memoization significantly reduce this number. The space complexity is driven by the recursion depth, which is k, and the size of the memoization table, which depends on the number of unique states. Several edge cases must also be handled. For instance, if there's only one piece, movement rules are simpler as there are no collision checks. If no moves are allowed, the initial configuration is the only valid state. On a small board, such as one of size 1 by 1, no piece can move, so again, only the initial configuration is valid. Lastly, pieces blocked by others must remain stationary unless the blocking piece moves, adding another layer of complexity. To understand this algorithm in action, consider an example. Suppose the chessboard is 4 times 4, with a rook starting at position 1, 1, and a knight starting at position 2, 2. If we allow 2 moves, the algorithm first generates all possible moves for the rook and knight over 2 turns. Using backtracking, it simulates every combination of these moves while ensuring no collisions occur. Each valid combination is counted, and the total number of such combinations is returned as the output. For this particular setup, the algorithm would calculate the total valid combinations to be x, demonstrating its ability to systematically explore all possibilities while adhering to the problem's constraints. Here, we start by importing the product function from the itertools module, which will be useful later for generating all possible combinations of paths. Then, we define a class solution that contains our main method count combinations. This method takes 2 inputs, pieces, which is a list of chess pieces, and positions, which provides their starting positions on the chessboard. Next, we define a dictionary called moves, where each piece is associated with its possible movement directions. For example, a rook can move horizontally or vertically, while a bishop moves diagonally, and so on. We then define a helper function called is_valid to ensure that a given position, represented by coordinates x, y, remains within the bounds of the chessboard, which is an 8x8 grid. After that, there's another helper function, generate_paths, which generates all possible paths for a piece starting from a given position. It iterates through the directions defined for the piece, moving step by step in each direction and collecting valid positions. These positions are stored as paths, which are then returned as a list. The generate_paths function returns a list of all valid paths for the given piece starting at its initial position. Using this, we generate a list called all_paths, where each element corresponds to the paths of a specific piece at its starting position. Next, we define another helper function, no_collisions, which ensures that no 2 pieces occupy the same square at the same time. It does this by checking if any position in the current state is repeated. If a collision occurs, the function returns false, otherwise, it returns true. The main part of the solution involves iterating through all possible combinations of paths using the product function. For each combination, we determine the maximum path length and simulate each step. At every step, we calculate the current positions of all the pieces. If any collision is detected, the loop breaks early. If no collisions occur throughout the simulation, we increment the count of valid_combinations. Finally, the method returns the total count of valid move combinations where no collisions occur, ensuring all pieces move legally according to their defined rules. Here, we start by defining a constant map, moves, which stores the possible move directions for each piece type. For example, the rook can move horizontally or vertically, while the bishop moves diagonally. The queen combines both rook and bishop movements, and the knight has its own distinct L-shaped moves. Next, the count combinations method is defined, which calculates the number of valid move combinations for a given set of chess pieces and their starting positions. First, we determine the number of pieces, then initialize a list called allPaths to store all possible movement paths for each piece. The generatePaths method is called for each piece, generating its potential moves based on its type and starting position. We also initialize a variable, valid combinations, to count the number of valid scenarios. The Cartesian product method is then called to generate all possible combinations of paths the pieces could take, which we will evaluate for validity in the subsequent steps. Now, we iterate through each combination of paths generated by the Cartesian product. For each combination, we calculate the maximum path length among all pieces. The main validation loop processes each step from 0 to this maximum length. At every step, we track the positions of all pieces using a set called occupied. For each piece, we determine its current position based on its path and step index. If the step exceeds the path length, the piece remains at its final position. We then construct a unique key for the position and check if it is already occupied. If it is, the isValid flag is set to false, and we break out of the loop. If no conflicts are detected, the position is added to the occupied set. After evaluating all steps, if the combination is valid, we increment the valid combinations counter. This ensures we only count scenarios where no pieces collide at any step. The generatePaths method is responsible for determining all potential movement paths for a given piece starting at a specific position. We begin by adding the initial position as the first path. For each direction in the piece's movement set, we simulate moving step by step along that direction. At each step, we check if the new position remains within the bounds of the chessboard using the isValid method. If the position is valid, it is added to the current path, and a copy of this path is saved to the paths list. This process continues until we reach an invalid position, at which point we stop extending that path. The isValid method ensures that the x and y coordinates remain within the range of 1 to 8, representing the boundaries of a standard chessboard. This guarantees that all generated paths remain valid within the context of the game. Finally, the Cartesian product method generates all possible combinations of movement paths for the given pieces. This is achieved using a helper method, Cartesian product helper, which recursively builds combinations by selecting one path for each piece at each depth of recursion. If the recursion reaches the depth of the number of pieces, the current combination is added to the result list. Otherwise, for each path in the current piece's list of paths, the path is temporarily added to the current combination, and the helper method is called recursively to process the next piece. After returning from the recursive call, the path is removed to backtrack and explore other options. This approach systematically explores all possible combinations of paths, ensuring that we account for every scenario where the pieces might move on the chessboard. Once all combinations are generated, they are returned as the result. Here, we begin with a simple scenario involving a single rook placed at position 1, 1 on the chessboard. Since we only have one piece, n is initialized to 1. A dictionary, moves, is used to define the movement patterns for each type of chess piece. In this case, the rook can move horizontally or vertically across the board. The generate_paths function is tasked with computing all possible paths the rook can take starting from its initial position. For the rook at 1, 1, it can move to the right along the first row, generating paths like 1, 2, 1, 2, 1, 3, and so on, up to 1, 2, 1, 8. Similarly, it can move upward along the first column, generating paths like 2, 1, 2, 1, 3, 1, and so on, up to 2, 1, 8, 1. Together, these paths represent all possible moves the rook can make from its starting position. Now that we have all potential paths for the rook, the next step is to simulate all possible move combinations. This is done using the product function, which evaluates every combination of paths. In this case, since there is only one piece, the paths are straightforward and sequential. For instance, the rook might move from 1, 2 to 1, 3, and then to 1, 4. At each step of the simulation, we ensure that no collisions occur using the no_collisions function. Since there is only one rook, there are no other pieces to consider, and it cannot collide with itself. As a result, all simulated paths are valid. Finally, we find that there are 14 valid move combinations for the rook starting at position 1, 1. This serves as the output for this example. In this example, we introduce a scenario with multiple pieces, a bishop at position 4, 4, and a rook at position 1, 1. Here, n is initialized to 2 to account for the two pieces. We begin by generating paths for each piece. The bishop moves diagonally, so starting from 4, 4, it can move to positions like 5, 5, 5, 5, 6, 6, and so on, depending on the direction. These paths extend until the bishop reaches the edge of the board. Similarly, the rook's paths are the same as in the previous example, as it starts at 1, 1. All paths for both pieces are stored in all_paths. Next, we simulate all possible combinations of moves using the product function. For example, the bishop might move to 4, 5, while the rook moves to 1, 2. On the next step, the bishop could move to 4, 6, and the rook to 1, 3. At each step, we check that the two pieces do not clash on the same square. To ensure that move combinations are valid, we use the no_collisions function. This function verifies that the bishop and rook occupy distinct squares at every step of their paths. Some combinations may be invalid due to collisions, such as both pieces attempting to occupy position 4, 5 simultaneously. These combinations are excluded from the results. After validating all move combinations, we determine that there are 198 valid sequences where the bishop and rook can move without conflicting with each other. Now, we move on to a third example featuring a single queen at position 3, 3. In this case, with only one piece, n is set to 1, and we proceed to generate paths for the queen. The queen is unique in that it can move in all directions, horizontally, vertically, and diagonally. Starting from position 3, 3, it generates horizontal paths like 3, 4, 3, 4, 3, 5, and so on, up to 3, 4, 3, 8. Similarly, vertical paths include positions like 4, 3, 4, 3, 5, 3, and so on, up to 4, 3, 8, 3. In addition, diagonal paths are created, such as 4, 4, 4, 4, 5, 5, and others depending on the direction. Once these paths are generated, we simulate all possible move combinations for the queen. For example, the queen might move to 3, 4, then to 3, 5, and then to 3, 6. Since there is only one piece, no collisions are possible, and all simulated paths are valid. As a result, we find that there are 56 valid move combinations for the queen starting at position 3, 3. To analyze the time complexity of the solution, we need to break it into its components. First, the time required to generate paths for each chess piece. For a given piece, the generate_paths function calculates all possible moves in each direction while staying within the boundaries of the chessboard. For example, a queen, which can move in 8 directions, generates up to 7 moves per direction, as the maximum distance on an 8x8 board is 7 squares. If there are n chess pieces, and each piece has an average of d directions, then the time complexity for path generation becomes O(n*d). Next, we have the Cartesian product of all paths, where we compute all possible combinations of paths for the n pieces. If each piece has an average of p paths, the Cartesian product results in approximately O(p⁻n) combinations. This step is computationally expensive, as the number of combinations grows exponentially with the number of pieces. Once the paths are generated, the algorithm performs collision checks for each combination of paths. This involves simulating the movement of the pieces step by step. The number of steps is limited by the length of the longest path, which is at most 7, the maximum distance on the board. At each step, the algorithm checks for collisions by comparing the positions of all n pieces. This requires an O(n) operation per step. Therefore, for a single combination, the collision check takes O(7*n), which simplifies to O(n). Since there are O(p⁻n) path combinations, the total time complexity of the collision checks becomes O(p⁻n*n). When combining the time for path generation and collision checks, the overall time complexity is dominated by the Cartesian product and collision checks, leading to O(n times d plus p⁻n times n). Here, d and p depend on the movement rules of the chess pieces, but for a given chessboard, these are constants, so the complexity simplifies to O(p⁻n*n). Now let's analyze the space complexity. The first component is the storage of paths generated for each piece. If there are n pieces and each piece has an average of p paths, the space required for storing these paths is O(n*p). The second component is the space used during the Cartesian product computation. Since the product *all_paths function generates combinations lazily, it does not store all combinations simultaneously, making its space requirement negligible. Lastly, during the collision checks, the algorithm maintains a set of occupied positions at each step. The size of this set is equal to the number of pieces, n. Therefore, the space required for this step is O(n). When we combine these components, the overall space complexity is O(n*p). Since p is constant for a given chessboard, this simplifies further to O(n). The overall space complexity of the algorithm is O(n), as we determined earlier. Comparing this with a brute force approach highlights the optimization achieved. A naive method would involve generating all possible positions on the chessboard for all pieces across all steps, which would result in an enormous search space of O(8*n*7). This arises because each piece could theoretically occupy any of the 64 squares on the board over a maximum of 7 steps. In contrast, the given solution intelligently restricts paths to valid movements of chess pieces, which reduces the search space to O(p⁻n). This is a significant improvement, as the algorithm leverages the movement constraints of chess pieces to prune unnecessary combinations. While it is near optimal for the constraints, further optimizations could potentially prune invalid path combinations even earlier, during the Cartesian product generation phase. Finally, let's look at the best, average, and worst-case scenarios. In the best case, the chess pieces have limited mobility, such as knights, which results in fewer paths per piece. This keeps the average number of paths, p, smaller, and the time complexity remains O, p to the power of n*n, but with a reduced constant factor. In the worst case, the pieces are queens or other highly mobile pieces, maximizing the number of paths, which increases p and makes the exponential growth more pronounced. Despite this, the dominant term in the time complexity, O, p to the power of n*n, does not change. The big O notation here reflects the fact that the exponential growth of p*n dominates all other terms. This is because the number of path combinations and the operations required per combination both grow rapidly with the number of pieces, making the algorithm computationally expensive for large n. However, the optimizations in the solution ensure that the problem remains tractable within the given constraints. A common challenge in solving this problem is ignoring the unique movement rules for each chess piece. For example, rooks can only move in straight lines, while knights have their distinctive L-shaped movement pattern. Failing to account for these rules can lead to counting invalid combinations. To address this, it's helpful to implement a dedicated helper function for each piece type that validates moves based on its specific constraints. Another issue arises with double counting moves. This happens when the same set of moves is treated as different permutations, such as swapping the order of two pieces making identical moves. To prevent this, always establish a systematic order for processing pieces to avoid duplicates. Lastly, overlooking overlaps or collisions, where two pieces occupy the same square or block each other, can invalidate combinations. A reliable way to handle this is by tracking occupied squares and ensuring no two pieces share the same position at any time. Now, another pitfall is relying on inefficient brute force. Generating all possible moves for each piece without filtering can quickly become computationally expensive, especially on larger boards, leading to time limit exceeded errors. Instead, you can employ pruning techniques, like backtracking, to identify and eliminate invalid paths earlier in your computation. Additionally, incorrect board boundary checks are a frequent source of bugs. Moves must always remain within the NX and chessboard, so you should include validation logic to ensure coordinates stay within the range of 0 to n1. This simple check prevents runtime errors and ensures your solution only considers valid moves. When preparing for interviews, it's crucial to understand the underlying concepts of this problem. It revolves around constraint satisfaction and combinatorial optimization, so identifying this early can help you choose the right approach, such as backtracking or depth-first search. Optimization is another key focus. Interviewers appreciate solutions that prune invalid paths early, like terminating a branch when a move creates conflicts. Scalability is equally important. You should be ready to analyze how your solution performs as the board size or the number of pieces increases. Highlighting time complexity, especially for large inputs like n equals 10,000, shows you understand practical limitations. Don't forget edge cases, such as having all pieces of the same type, working with a single square board, or handling dense placements on a maximal board size. It's helpful to explore related problems that share commonalities with this challenge. For instance, LeetCode 51, the n-queens problem, involves placing queens on a chessboard without conflicts, a combinatorial optimization task similar to this one. LeetCode 52, n-queens 2, builds on this by focusing on counting valid solutions efficiently. Other relevant problems include LeetCode 1219, path with maximum gold, which uses backtracking to navigate a grid under constraints, and LeetCode 980, unique paths 3, where you must find paths satisfying specific conditions on a grid. Studying these problems can deepen your understanding of the techniques and strategies applicable to this problem. Finally, let's compare different approaches and their trade-offs. Brute force involves generating all possible move combinations and filtering invalid ones. While simple to implement, it's computationally expensive, with a time complexity of O, k to the power of n, for k moves in n pieces. Backtracking improves on this by systematically exploring move combinations and pruning invalid paths early, making it more efficient, though it requires careful implementation. Dynamic programming is another option, leveraging memoization to store results of subproblems, such as valid moves for smaller subsets of pieces. While efficient for repetitive subproblems, it can demand significant memory for large boards. Lastly, bit masking is a highly optimized approach for representing board states and piece positions, but it's more complex to implement and debug compared to backtracking. Each method has its strengths, so the best choice depends on the specific requirements and constraints of the problem. Great job! We've explored the number of valid move combinations on chessboard problem, discussing key insights and an efficient approach to solve it. Remember, mastering problems like this strengthens your combinatorial and algorithmic thinking. Thanks for joining, and stay tuned for more coding challenges. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!